Hi logic students, I wanted to give you an example of a proof that is a bit more complicated than some of the basic examples that are in the textbook. This may be a proof that is more similar to some of the exercises that you do in the homework. So here we have an argument. I've already written it down to start the proof. The first premise is for all x, if px then qx. And the second premise is for all x, if qx, then rx and not sx. And we need to prove for all x, if px, then rx. Now, this is somewhat difficult to do unless you use a technique that is basically an indirect proof, or what some philosophers and logicians called reductio ad absurdum. This is the term. This is Latin for reduction to the absurd. What does this mean? It basically means that instead of proving the conclusion directly, you try to prove or you assume the negation of the conclusion. So we will assume that the conclusion is false, and then we will show that from that assumption a contradiction follows. So that will tell us that it's impossible for the conclusion to be false, so the conclusion must be true. So instead of proving that for all x, if px, then rx is the case based on these premises, we will show that not for all x, if px, then rx leads to a contradiction. Okay, so what you want to do is you indent the next line to mean that you're doing a kind of secondary proof, something that you set aside with respect to the main thrust of the proof. And this will be something that you start by assuming that the conclusion is false. So you will enter the negation of the conclusion. It's not the case that for all x, if px, then rx. And this is justified as assumption or assumption for indirect proof or something like that. Now, what you want to do is go from here and do all your transformations until you find a way to exhibit a contradiction. That is your goal at this point. That is, a contradiction will be two formulae that are one the negation of the other. So, for example, FA and not FA would be a contradiction. So we'll see what kind of contradiction we can come up with here. In the next step, we want to try and get rid of this negation that is in front of the universal quantifier here. It's never easy to work with formulae that start with a negation. So remember that you have that rule of quantificational equivalence. You can push the negation through the quantifier and move it to the other side, as long as you change the quantifier, in this case from universal to existential. So in this next line, we will enter there is an x, such that it's not the case that if px, then rx. And this is justified by 3 quantificational equivalence. Now we have to try and get rid of the quantifiers. Remember that you start proofs by trying to get rid of the quantifiers so that you have shorter formulae to work with. Here we have an existential quantifier, and here we have two universal quantifiers. So it's always best to use existential instantiation on the existentially quantified statement, because you know that there's that restriction that we have to introduce a new constant if we instantiate. So on line 5, we want to use existential instantiation and go to, so get rid of the quantifier and instantiate to a constant. So we can just pick A. So this formula on line 5 is an instantiation of line 4. The justification is for existential instantiation. Now let's see what we can do here on line 6. What we have here is a conditional. So something we can do is use the rule of disjunctive implication. Remember all the rules that we have, they afford us the opportunity to do many good things for our proof. And so whenever you have a conditional, you can rephrase the conditional. Look at disjunctive implication here. You can rephrase the conditional as a disjunction of the negation of the antecedent and the consequent. So anything on the form if P then Q can be rewritten as either not P or Q. So in our proof, we can rewrite if PA then RA as either not PA or RA. So we keep the negation and then we rewrite what's inside the parentheses as either not PA or RA. And the justification is 5 disjunctive implication. So that rule over there, here under more equivalencies. In the next step, step 7, we continue to work with this formula. So let's see, what is it? It's a negation of a disjunction. It's the negation of either not PA or RA. And remember that you have an equivalence that you can use in these cases. It's called one of De Morgan's laws. You can see it here. This goes both ways. So if you have the negation of a disjunction, in this case not P or Q, you will rewrite it, or you can always rewrite it as a conjunction of the negations of the two elements of the disjunction. So anything on the form not P or Q can be rewritten as not P and not Q. Okay, so let's do that. We can convert this to not PA. So remember that we have to make a conjunction of the negations of the two elements of this disjunction. But because this element, the first element in the disjunction, is already negative, we will stick a second negation in front of it. So not PA and not RA. And this will be 6 De Morgan. It's one of the laws of De Morgan, who was a British logician. The next step is simple. Whenever you see a double negation, remember that you can get rid of it. Two negations cancel each other. So here you can simply rewrite this formula without the double negation in front of PA. You just write PA and not RA. And it's 7 double negation. Oops. Okay, and here things are beginning to look good, if you think about it, because we have worked our way to a conjunction. And conjunctions are easy to work with because you can use the rule of simplification and just break them apart. Obviously, if you have PA and not RA, this formula entails both PA alone and not RA alone. So you can use simplification and make PA by 8 simplification, and also in the next step you can grab the not RA by itself, also by 8 simplification. And now we can finally get some serious action with those two premises up there that we still haven't used. We basically have just used the assumption that we made here that the conclusion was actually false. We assumed the contrary, or the negation of the conclusion. Now we can instantiate those two premises, and you'll see that things get easy at this point. So with line 11, I'm going to instantiate premise 1 using the constant A and using, obviously, universal instantiation. So now I have, if PA, then QA. By line 1, universal instantiation. And while I'm at it, I can do the same thing with line 2 and instantiate this conditional all to the constant A. So line 12 will be if QA, then RA and not SA. Again, to universal instantiation. Okay, I'm going to go over to this side, but keep in mind that we're still in this kind of indented area. So looks like I'm running out of time here. Videos can only be 15 minutes. So let me pause here, and I'll just make another video with the rest of the proof, but we're very close to finishing this. So I'll see you in the next video.